Hello? Is this microphoning or not? It is? Okay, cool. This isn't recorded, is it? Oh, nice. No, that's cool. That's cool. Oh, yeah, that'd be sick. That'd be sick.
You just click you can just leave it here or leave that one.
Yeah.
Your back.
Yeah, cool.
Yeah, that should work.
That's good. Nice.
And that's all you need. Usually start this is what one and a half minute effect. So start in 3 or so minutes.
Okay, cool. No, it's fine. I'll just introduce myself. Yeah, that's fine. I mean, you can introduce me if you want. I don't really have a bio, no.
Excited to introduce Dylan Patel. He's the founder and CEO of Semi-Analysis, and a lot of you might know about him through his social media accounts, specifically Twitter, and the blog post that he has, sharing a lot of cool insights about chips and hardware and how the industry is moving. So thank you for coming here, and we're excited to hear about your thoughts.
Awesome, cool. Thanks for having me. I'm going to talk today about inference math, our simulator for it, and then generally AI megaclusters. And the order will be backwards, right? It'll be first megaclusters. But quick intro, right? Semi-analysis. We do a bunch of research on the industry, technical and market analysis related stuff, like supply chain. Companies sort of globally distributed, and we have people who've worked all the way from ASML to Microsoft and Tesla. So kind of a bunch of people that are technical in that space, globally distributed, covering semiconductors, and AI and ML systems. And so first we're going to talk about AI data centers, specifically what everyone is doing with those. Then we're going to talk about inference math, tokenomics, right? How how inference systems work, various optimizations. I'm going to talk about OpenAI's O1 and how that really changes inference from a systems perspective, not like a workload or usage perspective, but from a, hey, how does this impact the system of inference? Talk a bit about our inference and training simulators, and then maybe cost of ownership of sort of a cluster. So starting off with is AI megaclusters, right? This is sort of what's currently state of the art. And this is specifically Microsoft's data center in Arizona that's used by OpenAI, right? And so each of these buildings is 48 megawatts. 48 megawatts is a load of power. A typical household in America uses 1 to 2 kilowatts, right? So we're talking about a couple orders of magnitude. And Each of those, each of these buildings has roughly 32,000 GPUs. And they have a bunch of networking in between them. And then they also have networking between each of the buildings, so you can get to roughly 100,000 GPUs. And so on the right, you can see sort of the physical manifestation of like how it's deployed, right? Like there's 32 servers with 256 GPUs. That's like the base block that you deploy throughout the data center. And then those are connected up to switches, which are in red on the right. And then those are then connected to each of these other blocks, through further layers of networking. And there's some interesting things about their networking, right? You have like front end networking, you have back end networking in an ML system. So your front end networking is like how you connect to the internet, to storage, to management servers, these sorts of things. Then you have your back end network, which is really specifically optimized for doing your all reduce and doing your various collectives there on the actual ML model, right? Not bringing in data, but like and then one of the interesting things that's here is if you see on the bottom right image, there's like a couple different like types of networking topologies, right? You can do fat tree, which means like everything like kind of groups together and it goes up like a fat tree. I don't know. I think that's the like easiest way to describe it. Then there's rail optimized, and like the interesting thing there is like if you look on the bottom in the bottom right, that image has a lot. Like each server goes to many different switches, and then it sprays out further, right? And this like increases the reliability of a cluster, right? So if you go back to this, right, a fat tree would have 4 of these servers in one rack connect to one switch, right? And then they'd go to the next layer of switching. Whereas oh, you can't see my mouse. Whereas a rail optimized server will have each server connect to 8 different switches. And this sort of lets you lose any individual switch and still continue your ML workload. So that's the typical way that it's built. But that's sort of like quote unquote last generation, right? That Arizona data center is building quote unquote GPT-5, right? That caliber of model. But the next generation of models is that people want to continue to scale. There's fear scaling laws don't work, but that's probably not true. People are still trying to scale really fast. So this data center, right, is each of these is 48 megawatts, and you can see horizontally like that's that one data center. Here you can see that same data center, that same type of data center vertically, right? And that's 48 megawatts, or 57, right? And then this data center is like 300 megawatts. So there's a completely different density of power because it's specifically built for AI, right? And AI is significantly more power dense than a standard CPU data center. And so this is like a huge leap forward, but then, that's just that bottom right corner is 300 megawatts. But Microsoft has placed a lot of permits and stuff to build 4 of those 300 megawatt buildings. And so the scale that they want to reach to, 1.5 gigawatts in 2.5 years in one site. Now, the interesting thing is that like each GPU takes roughly 1,000 watts to 1,400 watts, right? So if you do the math on that, 1.5 gigawatts is like 1 million GPUs, right? In rough terms. So this is like a humongous scale up in compute, right? Because GPT-4 was trained with 24,000 GPUs roughly, and GPT-5 is on the order of 100,000. And then they're trying to build this data center over the next few years that's 1 million, right? And that's like, a significant increase in scaling. But the important thing is that like, that's not enough scale for what people want to build still, right? 1 million chips at once. Because very few locations global, or in the US at least, can have a gigawatt delivered to it in a fast enough timescale, right? The servers are being manufactured, and power generation is very difficult to do. Power interconnection, right? Power plants generate power at like hundreds of thousands of volts AC, and chips want 48 volt DC to go into the server board. So you have to do a lot of like switching of power to get it to the right format for the chips. And so what's interesting is that people are not just trying to do training on one site, right? Not just one building. We already scaled past one building because that's like 24,000 GPUs. The Arizona one was multiple buildings. But people are trying to move beyond just like one site because they want to scale the models extremely fast because they believe in AGI, right? And they think that this is one reasonable way to get there. And so Google's like actually publicly stated that they've done this, right? They've trained across multiple data centers in a region, right? And there's many ways of doing that, right? But typically today, when people train models, they do what's called synchronous gradient descent, right? The various GPUs will do a bunch of work, and then they'll work together, and then they'll like communicate the results to each other, right? So this is synchronous. But to scale GPU like runs to the millions of GPU scale requires moving past synchronous gradient descent, right? Because you're going to have all these issues with regards to like timing everything. If one worker or one replica fails, then everything, the entire cluster fails. There's a lot of reliability challenges. Also, if you want to scale beyond one single data center to multiple data centers, there's latency issues, there's networking and bandwidth issues connecting these data centers together. So a lot of the research being done now by the big labs is working on asynchronous updates. And so what that sort of means is there's like a few different ways to do that. But basically, the work is done, it doesn't have to be synchronous, right? You don't have to update every single step. Instead, you can do, there's a variety of different like methods, right? There's hierarchical SGD, and then there's parameter servers. So on the left side, it's sort of like there is a diagram of a parameter server, right? So that's a server that like kind of keeps all the weights that are like the ground source of truth. You send them to various data centers or various compute blobs, right? So thousands of GPUs, tens of thousands of GPUs are doing a bunch of work, and then they'll send the update that they have to the parameter server. And so this is like one method of people moving past synchronous. Another method is like hierarchical. And so this image on the right, the left, your right, is showing the difference between synchronous versus hierarchical, right? And so you see there's like these stragglers, right? So if you look at processor 2, processor number 2 is a straggler, right? It's for some reason working slower or didn't complete its job, right? Hardware is very unreliable, so it'll just do that, right? Especially when you're talking about like the magnitude. So there's some element of compute that is a straggler. And in standard SGD, everyone is held up by that one bad worker, right? And that's like wasting a ton of money, right? If you're talking about, hey, going back to this like data center, right? This data center is 300 megawatts. It has 200,000 plus GPUs. Each GPU is like $30,000. You're talking about billions of dollars that could be sitting idle because one GPU is like slow. It's a straggler, right? So you want to move past that and like move to something where, hey, if there is someone that's a straggler, you still continue to do the work as fast as possible, right? You don't wait for them. And so there's a lot of research going on for this, a lot of interesting papers out there on archive that can be read about sort of different ways of moving past synchronous training. But the interesting thing is like, if you are OpenAI and Microsoft, or if you're any of the other labs, you have real challenges growing your compute extremely fast, right? And so therefore, one of the things you do is you try and tie together data centers, right? Because each individual data center can only build so fast. And so, that's what they're doing, and they want to connect multiple data centers across the nation, right? You want to be able to use your old data center for the last model. You want to be able to connect data centers that you're building now across the U.S. To train very, very large models, right? So, I showed earlier the Wisconsin one, but there's a similar data center in Atlanta, right? Or a similar thing that they're building right now in Atlanta. And it's the same thing, right? It's like, hey, like there's these huge data centers, continue to build them, tens of billions of dollars being spent on this side as well, and it will grow to be very large, right? And you're filling it with GPUs, and you want it to work more in that direction. And the same applies to like other data centers, right? So OpenAI can't get enough compute from Microsoft, so then they're also going to Oracle, right? And Oracle's building, another, gigawatt scale data center eventually, right? And again, a gigawatt is like 500,000 plus GPUs. That's billions, tens of billions of dollars. So OpenAI signed a deal for just 200 megawatts. So that's 4 of these buildings, right? With Oracle. And this site is going to be a gigawatt. So for 1/5 of the site, they're paying something like $12.5 billion over the next 5 years, right? So this is an extremely large amount of money that they're spending on just one specific site for training. And so this is really, really important because, think about like, hey, if you can improve the efficiency of this by 1%, 1% of, $12.5 billion is a lot of money, right? It's also a lot of power, a lot of energy, a lot of, it'll make things happen faster, right? This is a huge area of like improvement, and probably a lot more important, at least in my eyes, than any sort of algorithmic like level like change is like, hey, can we make these systems more efficient that we're building? Or can we make the systems that are being tied across the nation more efficient? And so the same applies to like companies like Google, right? They've also got like many very large data centers, except they don't use GPUs, right? They use TPUs. And TPUs have a very advanced design, liquid cooled and all these things. And so, Google's data centers look very different from the Microsoft ones. Could dive into why, but like basically like if you see on the right side, the right side, you have all these like chillers. They're just basically there to like cool water down because then you feed the cooled water to the chips. And then they warm it up, and it's like a loop, right? The data center looks very different, like very dense, right? Microsoft's data center is Google's data centers are much smaller for the same amount of power because they do all this liquid cooling, right? And the interesting thing is like they also like have run into the same problem of like, hey, can't get enough power on one site, so instead we're just going to connect like 3 different data centers together, right? And that's in Ohio, right? And then in Iowa and Nebraska, they're going to do the same thing. Right? They have these various data centers. They can't build them fast enough, so they're going to connect them all together to try and run a very large training run, right? Because and this is all still like in the research phase, but they're also doing it physically, right? They haven't figured out how to do asynchronous training yet, but they hope to be able to, or they figured out a little bit, but haven't like been able to scale it up. So it's really very much like a YOLO, right? Like we're going to connect all these data centers together and hope we can figure it out. And so like in Iowa and Nebraska, they're doing that with 4 different data centers, right? And this is like one method of like trying to scale models as fast as possible, right? Build the biggest data center you can, and because each individual site has limitations in terms of like grid interconnections and power, then build a bunch of different data centers and connect them together with fiber and try and figure out how you can train across them. The other option is like what Elon is doing, right? And Elon is like pretty crazy, because like what he's doing is like very non-conventional. So they bought a factory in Memphis, right, Tennessee, which is interesting. And this is like an appliance factory, right? It used to make like washing machines before it got shut down, right? And it's been shut down for like a while. So they bought a washing machine factory and converted it into a data center. But like the reason they bought this factory is because right along the side of it is a humongous gas line, right, which goes to a huge gas power plant. And instead of like tapping the power from the gas power plant, which they're trying to do, but the grid interconnections are like very slow, right? So you can see in the yellow that there's 150 megawatts that could come from the grid, but that substation, the transformers and such, are not built until next year. And he doesn't want to wait till next year to start training his, humongous models, right? So instead, he does like something incredibly different, right? He taps that main gas line and buys a bunch of mobile generators, right? Rents them, buys them, whatever. Some of these are for like disaster relief and things like that, right? But like he's just like got mobile generators plugged in to the main gas line and then converted this factory into a data center. And that's those red ones are one model, and then that green one is another model. Different models of like mobile generators, because no one has just a bunch laying around, right? So just get whatever ones you can. And then all those trucks on the bottom, on the back side of the factory, right? Not the parking lot, but the other side, are chillers, right? So they just cool water down. So like it's interesting. These are all like mobile chillers as well, right? Like you see, they're all just like semi-truck, like there's like 60 of them, right? Versus like what Google does is like very like, what Google does is like very purpose built, right? Like you can see those chillers look, not much to describe besides like they look reasonable, right? They look like they're engineered for this purpose, whereas like this is clearly not engineered for this purpose, right? But it's all about how fast I can get the model out there, right? So if I can get 100,000 GPUs working this year, then I am now competitive with, at least on a compute standpoint, with OpenAI and Google, right? And so the speed of what they're doing is interesting. Oh, the other thing is like they're deploying a Tesla Megapack, like a big battery pack thing, because the grid started complaining that they're like like pulling power rapidly and then like not pulling it, and like that fluctuation on the grid is like making the grid like fail in some ways. So they're now putting like a battery pack, like a massive Tesla battery pack, to like smooth out the power that they draw from the grid. What's interesting is like this is the first deployment of NVIDIA GPUs that is water cooled, right? Everyone else has done primarily NVIDIA GPUs that are air cooled, and next year they'll do water cooled NVIDIA GPUs. But this is the first like large scale deployment that is water cooled of NVIDIA GPUs, whereas before only Google did water cooled TPUs, right? Everyone else is using air cooled servers, which is less efficient, less dense.
Is there any particular reason people don't do water cooled?
It's just expensive. The supply chain is complex. There's more points of failure, right? Like putting water next to electronics it's kind of hard, And feel free to interrupt if you have any questions. Thank you for interrupting. Yeah, go ahead.
What's the best approach we have for fixing the latency issues with like multi-data center distributed stuff? There's DeLoco, right? But are people doing anything better for updating like with like less latency?
So latency is not an issue, right? So if you look at the Llama paper, right, Llama 3.1 paper, they talk about how long their training steps take, right? And it was roughly every sort of batch would take like 10 to 15 seconds. And then they would synchronize all the servers, do SGD, whatever, and that would take like another 1.5 to 3 seconds, right? So like on a relative basis, I can send a packet from here to New York in like 150 milliseconds, right? So it's not really a latency thing, right? Like if you were to just say, oh, it takes 10 seconds of work and then 2 seconds of communication, adding 100 milliseconds of latency for communicating from here to New York is not really an issue. It's about the bandwidth, right?
Okay, but it is you still need the bandwidth for like updating stuff on the local workers first, and then.
Right. So when you look at like LLMs, right? Like most people use AtomW, right? And AtomW as an optimizer is like 4 bytes per parameter, roughly, if I recall correctly, the optimizer state. And like if you're transmitting all that, right? You train a 100 billion parameter model. You end up saying, hey, there's 400 gigabytes if this is all in if it's all in FP8. There's like 400 gigabytes of data that you need to transfer every step, right? But people aren't doing this for 100 billion parameter models. They're doing it for like multi-trillion, right? So let's call it 10 trillion parameters, 4 bytes per parameter. That's 40 terabytes of data you need to transmit in like 2 seconds. So who has 20 terabytes per second of bandwidth? So you have to move past using like AtomW-like optimizers, right? You have to move to things like DeLoco or there's a lot of other stuff out there. I'm not actually sure what people are doing on the leading edge exactly, but there's a lot of different ways to try and a lot of open research there. And nothing is like a silver bullet that like clearly works as good as synchronous training. So yeah, supply chain for water cooling is very complicated. And there's a lot of risk with regards to like leakage. There's a lot of risk with regards to cost, getting people to build all the things, right? Like there's just all sorts of challenges, and it's a little bit more expensive, right? And so that's a challenge. The other thing Elon did was like he used Ethernet instead of InfiniBand. I don't know if that's like worth like talking a lot about. But there's like a variety of like different like things that you could do to build as fast as possible. And so like Amazon is doing the same thing, right? Like they're building like 12 data centers at the same time, right? If you look at this site, all of these are being constructed at the same time on the same site, right? Or 7, sorry. And if you look at like what Meta is doing is they used to have like this old data center, which is really cool because it looked like an H, right? But it was like very like bad compared to Google data centers, right? It's twice as big or almost 3 times as big, takes way longer to build, and it has less power capacity, right? But then when you look on the right, this is their new data center, right? And so this new data center has a bunch of, if you recall looking at the Google data center, on the right side of it, there's a bunch of these like water chiller equipments, right? They're not using the trucks like Elon, they're using like actual purpose-built water chillers. And so, one of the interesting things is like the type of data center you build is like really relevant. So Meta built this H data center, right? And then they tore it down. Like they were literally building it, they tore it down, and then they built the new one in the same spot because they realized, oh God, I want to make models. I don't want to make like standard CPU storage, like recommendation system, like brain rot algorithm, like things. So they wanted to make AI instead, and so they had to destroy their old data center and make a new one. before they put any chips in it and stuff. So there's a lot of drastic actions to be done on that regard. So this is like first half talk, I guess, is all about data centers, or first quarter of it. But I'm going to talk about inference stuff. So if anyone wants to ask about data centers, go ahead.
Why did they build it in H in the first place?
Sorry?
Why did they choose to make it H in the first place?
Yeah, so like the whole idea here is that like you have 4 data halls, right, where you do actual like servers, and then the center has all the networking. And because they were focused on building like CPU and storage and like inference systems that didn't have massive models, right, for recommendation systems, they didn't have extremely high density power, right? So going back to this rack right here, right, this is 80 kilowatts in a rack, right, 80 kilowatts in a rack. The typical rack at Meta in the H data center was like 12 kilowatts, right? So like it's 1/8 as much power in the same physical footprint. And that's, obviously if you increase the power a lot, you need to water cool it. But on the flip side, right, if you're using like CPUs and storage, like an SSD does not take a ton of power, right? A standard CPU doesn't take a ton of power, but a AI chip like an H100 takes a ton of power. So sort of they needed to make it much more dense. Also the fiber connecting all these servers together, the fiber's not expensive, but the optical to electrical conversion and back, it's called a transceiver, optical transceiver. Those are really expensive. And the cost scales with length, right? So getting a transceiver that sends 800 gigabits a second, 50 meters is much cheaper than 800 gigabits a second a kilometer, right? And so having a very large data center was fine because it's cheaper to build, right? And it's much, it doesn't need as much power density because you didn't need to have a bunch of high bandwidth interconnects between all your servers in an old school data center. But in AI data centers, you do because you're constantly sharing you're constantly doing SGD. Yeah.
Any other question? I know that some companies like Amazon, Google, Microsoft, they make their own like AI chips. So does what kind of chip they use affect how they build and design the data center?
Yes, absolutely. Because Google's had a design that has a completely different network than an NVIDIA chip, right? So NVIDIA chips have a network between 8 chips on a server, and then they use InfiniBand to connect to servers outside of it, right? Whereas Google has always had sort of this like other network, which is like in a rack of 64 in a rack of TPUs, you connect with like their special interconnect. So the networking is very different, and so like how you build your data center is very different. And Google's density was much higher, right? And so that's why they did water cooling. And it didn't make sense to do very high density for anything besides ML workloads, but Google knew that ML workloads needed a lot of high density, so they've always planned for this. Yeah, I think, yeah.
How is the grid supporting all this influx of power? And the second part to that, what do you feel about like big tech starting to like revive old nuclear generators like them just pushing towards nuclear power to support AI?
I mean, all the nuclear stuff is all just like marketing. It's not true. Like there's no real nuclear powered data centers. And the one that Amazon's trying to do keeps getting delayed for regulatory reasons. So like they sign these deals that are like not real. Every data center that is being built is it's primarily backstopped at least by natural gas, right? Like you can say it's, like you look at the sustainability reports, it says they're renewable powered. But like data center power consumption is like this, and renewables are like this. They don't turn off the data center, right? There's natural gas somewhere, or coal even, but usually natural gas. And there's certain data centers like in Texas where there's a natural gas plant in the middle of the data center, right? Like they've built, like CoreWeave has data centers like this, where there's just a bunch of data centers around a natural gas plant. So the power generation is not too difficult if you're fine with natural gas. The real difficulty is like converting it, right? And so like building a substation, like if you were to order like a substation today, it would take like 3 years to be built. And so it just takes so long because the US power grid has been like this for decades. The European power grid has been like this for decades, right? Like the Japanese power grid has been like this, right? Like the Korean power grid's been like this. Only like China and like India and Indonesia, like their power grids have been growing really fast. But like Western, sort of quote unquote Western power grids and the supply chain for them, right? Building the transformers, the switchgear, substation stuff, all this sort of stuff, supply chain has never had to deal with expansion. And now all of a sudden, AI, data centers want to go from like consuming 2% of the power in the US to 10+% in like just a few years. And it's like that, the supply chain is just not geared up to build this stuff as fast.
Question about microgrids. So it seems like a lot of these companies are ambitious in their infrastructure, like literally putting backup generators on the parking lot. Why would a microgrid solution not be a way to kind of like jump the line when it comes to grid interconnect and some of the regulatory issues?
Yeah. I mean, there is some of that. Turns out microgrids are still heavily regulated everywhere except for Texas. So there are challenges, but people are trying to make microgrids, right? Like the Amazon nuclear data center that there's been a lot of media about. That's supposed to be a microgrid. It's not supposed to go onto the grid, but it keeps being blocked for regulatory reasons. Like residents are like, oh, my power prices are going to increase, so don't do this. Things like this, right? So it is a challenge, right? And generally, you don't want to be co-located with your power if it's dirty, because you as a big tech company give the illusion that you're clean. But in reality, all of your data centers at some point are powered by natural gas. You just happen to buy these things called PPAs, power purchasing agreements, where like, oh, I'm going to buy a gigawatt of solar and then I'm going to build a gigawatt of data center, but like the solar is like not providing the actual electrons that are generated to run the chips. So like by not having it co-located, you also get to pretend you're sustainable still. Which is fun. Some companies have given up on their sustainability pledges. Like Microsoft quietly removed it from their most recent ESG report. Some of the ones around data centers. So it is microgrids are happening. Renewables are good, but like they're not really. It's hard to it's either build AI as fast as possible or like maybe mess up the environment a little bit. Go ahead.
You think there's going to be more XAI style, like hastily kind of move all the like coolers and the generators to kind of an unexpected place? And do you think more people are going to try to follow in the footsteps of that?
Sorry, I'm gonna pull this up because it's fun. Whoops. Multi-data center training. Where is this? Yeah, so here's like the CoreWeave data center is referring to. So in the center is a natural gas plant, right? And this is like completely reasonable, like if you're just not going to greenwash it, right? It's completely reasonable to build it as fast as possible. But the challenge is like you're a big tech company. Your employees care about like sustainability. They don't even want you doing like government contracts. Your shareholders care about this. You're like general perception matters, right? Like you've already got bad enough like perception from like ruining young people's minds that like just messing around. I also scroll a lot of social media. You don't want to like. I think there's just like a large like element of like, no, we're clean, we're renewable, we're green. Like Apple does this too, right? Like they're like, yeah, we're completely renewable, and then it's like, yeah, but like you're dumping like your supplier's dumping toxic waste in like a river. It's like, yeah, no, that's not us, right? And this is like the same thing, right? So like CoreWeave's biggest customer is Microsoft. Over 90% of CoreWeave's revenue is Microsoft, and CoreWeave can do this, but like Microsoft can't do that, right? Because that would be bad PR. So it's a bit of like Elon doesn't care, right? Because like if anyone's like you're not green, it's like I'm building electric cars. Shut up, right? Like so it's like a little bit of a different vibe there. I don't think people will do crazy stuff like XAI.
What do you think about the people putting like data centers on boats or underwater?
Silly. So the thing about GPUs is that they fail a lot. You buy a good chip from NVIDIA, and then it ends up failing like constantly, right? Like when you just install the servers and you like burn them in, it's called a burn-in. You just run a bunch of workloads on it, not actual real workloads, just like to test them. Like 4 or 5% of them die on turn-on, right? Within like the first 2 weeks, and you have to like switch them out and like all this. And then over time, like they continue to fail like slowly. So like if you put them on a boat, who is going to live on the boat and like swap stuff out? Same with space data centers. Like it makes no sense. Also like you have to generate power, and like grid stability is like having a lot of different stuff on the grid is how you get a stable like power generated, right? Otherwise, if you're on the ocean, you're also just going to be burning natural gas, right? Like so it's like not really any there's no benefits, right? So who's going to live on the boat and replace stuff, fix it, ship the new GPU to whoever and get new ones back, or networking cables or whatever breaks, fixing that, like that's difficult on a boat.
Do the burn-in and test that the chips work before they buy them?
NVIDIA does that for smaller players, but the big guys, they'll burn it in themselves and NVIDIA will replace it, but like they'll do their own test because they think their own tests are better. And if you can weed out like another percent that is going to die over lifespan initially, then it's like more stable for your users, right? Like if I'm like Microsoft and I'm deploying to OpenAI researchers, they're going to complain to me that the cluster's breaking. They're not going to be like it's NVIDIA's fault. So it's my job to make sure that like I weed everything out bad before I give it to the researchers.
Follow up to this gentleman's question, he mentioned about the UDC, the underwater data center. I think since last year, there's one has been used in China, South China Sea. I think they just put this under UDC near the land.
Yeah.
Probably they can, solve the cable and whatever, the replacement.
Yeah, Microsoft also did this for a bit, but then. Yeah. Yeah.
Is this something we can,
I think like the biggest challenge is like, again, reliability of these chips, right? Like for example, XAI's data center, they built this massive data center really fast. They had a random fire the other week. Like, I'm not joking, they had a fire in the data center. It's not that big, but they had a fire. Like, who's going to go put this out? Like, okay, fine, it's underwater, right? But something's going to break. Something's going to break, right? Like, something will break. It's like the most complicated thing people make is like chips and servers and connecting them together and fiber optics and cooling and all this stuff is very complicated. A lot of mechanical stuff, a lot of electrical systems. Things are not perfectly reliable. They will break. So how do you deal with that issue? I think it's perfectly fine to do that with like CPU and storage because CPU and storage is much more reliable than AI systems. AI systems are pushed to the max and therefore they also fail a lot more often.
An ideal way of building data center? Because right now different companies, they have different way of building, right? Because it depends, lots of components, including chip, server, whatever. Did you have any like quick summary for building this?
Yeah. I mean, I would say there's like an article on my site that's like mostly free that you can read about like the electrical infrastructure differences between like Google and Microsoft and Meta and how they build data centers. I think they all have their own unique approaches, right? Like these buildings are not like cookie cutter, right? Like Meta only deployed this H for like 8 years straight, right? Only this H size building, and then they moved to this new design. All of Amazon's data centers still look like this, right? The Microsoft one, also like the Google ones all look quite different, right? They have a bunch of different designs because they put a lot of special care to it, and they have a lot of engineering reasons why they've done that. But like the Microsoft ones are like these, for like 10 years, they only built data centers that were these rectangles, right? And the way they organize the servers, the networking, the cabling, the cooling, it differs across all of them. There's no optimal way. And they're still constantly experimenting, seeing what's better, tearing down old ones and, replacing it with a new one because it's easy to build a building. It's hard to build the grid interconnections. So they're still constantly experimenting on what's the best optimal way. Definitely a lot of innovation to be done there. Yeah.
I was just wondering, do you think the emphasis will shift from GPUs to FPGAs, RDAs? And if that happens, how will the data centers change? How will the energy change, the design change? And like, what do you think companies like Samino are doing for that?
I think that FPGAs are definitely not the way. I think like kind of segues quickly into like sort of inference math and like tokenomics, but like maybe I'll answer that like in a bit. I think there's one more question, or yeah.
Do you think the manufacturing of the chips is going to be able to cover the expected increase in demands for data centers?
Yeah. I think the supply chains are expanding really fast. There's always like random bottlenecks when you expand. Right? Sometimes it's the chip, sometimes it's the memory, sometimes it's the cabling, sometimes it's the fiber optic, optical transceivers. It can be the grid substation level stuff. It's all sorts of different bottlenecks, but everyone's building as fast as they can. Generally, like everyone will say that their stuff is like in short supply and they need to build more, and they're all expanding. But definitely, like there's enough for like million chip clusters, next year or year after type stuff.
When like CoreWeave built the data center on top of the natural gas, like what happens if like the natural gas runs out? Or does that just not happen?
I think a lot of catastrophic things happen when the sun stops shining and the gas stops flowing. I mean, generally, like natural gas is like pretty reliable. I mean, human civilization runs on fossil fuels, right? It's been pretty good for energy. I don't know. Yeah. Cool. Sorry. So yeah, I guess I'll segue to inference and like tokenomics and why this matters a lot, right? Inference providers, they're basically providing a token factory, right? Like in many cases, it's like the model company that's providing tokens via an API, access to an LLM, access to intelligence. But in many cases, it's like a third-party company that's offering this, right? And there's many optimizations here, quantization, batching, parallelism optimizations, et cetera. An interesting thing is it like dramatically affects your cost basis, right? So like if you look at this table, right, like if you have two H100s, this one's with Mixtral, which is like, I guess, an outdated model that no one uses now, but, sorry, it changes fast. The H100s, like, generally cost like $2 an hour, right? And so two H100s cost like $4 an hour, right? But then like how many tokens can you get out of it and how many can you sell to users is like very important, right? And so there's batch size, which is how many concurrent requests you're handling at once effectively, right? And so you have to batch at high enough of a level to actually like make profit. Otherwise, you're losing money. And so a lot of people who are serving tokens are actually just losing money because they're not serving enough users. And like there's various optimizations like, hey, quantization is great, right? Like you serve a lower quality model in many cases, but you save massively on memory bandwidth and power per operation, right? And so you end up with like this is efficient. Or like batching, there's humongous advantages to batching users together, right? There's humongous, there's like a curve, right? Of like, hey, if I only have one user on the server, I have really fast throughput for that user, right? It's like a great user experience. They get all their tokens out like really fast. If you're going on the opposite end, which is like I'm just serving tons of users together, they're gonna have a horrible experience, right? It's gonna be very slow. And so batching is like very important. But then there's like a sort of challenge when you're doing batching, right? Which is when you're, there's the model parameters. You have to read all those into the chip every single forward pass, every single token generation. But you also have to read each individual user's KV cache. And that KV cache is like very difficult. I'm gonna skip this parallelism stuff because whatever. But yeah, KV cache stuff is really important. Because that's like basically what's storing the state of your model, right? For that individual user. And the interesting thing is, I don't know if you followed like the calculation or looked into transformers much, but sorry, I don't know what this class has covered, but
Hopefully everyone is very comfortable with this.
Nice, cool. So there's like one optimization that like people have done, which is called group query attention, right? Without it, your formula is this, right? But with MQA, GQA, which are like standard optimizations for transformers now, you dramatically reduce your KV cache size per user, or your compute per user, right? And so when you switch to GQA, you get a humongous difference in how many tokens per second per user you can get versus the batch size, right? So if I'm batching 32 users, then I need to read each of their individual users' entire KV cache every step, which means that there's a humongous impact to how much, to every other user, right? Because you have to not just read the model parameters, but also the KV cache. And if I'm reading 32 different people's KV caches, then there is a significant drop in performance for each individual user. And the other interesting thing is like as you scale sequence length, right, your memory requirements soar. And this is even with GQA, right? So this is for Llama 3.1, 405B. But with a batch size of 64 on 8 H100s, at FP8, you run out of memory, right? At batch size 64 with a 40K sequence length, right? So if your users were submitting small prompts and getting small outputs, then you could batch much higher and you'd be much, much more profitable. But if you're doing very large prompts, then you can't serve as many users. And so sort of like when you look at inference API pricing, in many cases, you're getting charged different prices for inputs, different prices for outputs. In the case of like Google, for very long prompts, they charge a different price than for very short prompts. And this is because of the KV cache sort of requirements and that forcing them to batch at lower rates, which then subsequently forces them to not have as much, as many concurrent users and therefore serve less profitably. So they need to charge each individual user more. And this is really important because with reasoning models like OpenAI's O1, the average sequence length grows a lot, right? Now with like, there's many forms of like, doing inference to scale test time compute, right? To improve models. But what OpenAI's O1 does is it primarily the model reasons for a while and then it outputs, right? It does a much longer sequence length, right? If you ask it to like generate a web scraper, in the standard one, it'll just start outputting code and it'll be maybe like a 4K sequence length, right? But in O1, it'll think for a while and then it'll output the, code scraper. It'll be a better answer, but the sequence length may be like 40K. So now you batch much lower, and this is why OpenAI charges a lot more money for their O1 model, even though it's the same size as their 4.0 model. They charge 3 to 4x more because they believe that this is like a maybe there's some of this is margin too, but there's a big chunk of, hey, it's just that much more expensive to run. And there's a lot of optimizations that can be done, right? Flash attention, page detention, flash decoding, all these various sparse attention mechanisms, tons of quantization stuff, MQA, GQA, blockwise decoding. There's a ton of stuff here that there's been a lot of research from Stanford as well, right? I think striped pain and SSMs are both from Stanford. There's a ton of awesome research coming from Stanford as well as others, but each of these is like a huge optimization that could improve inference costs massively, right? I showed earlier how much GQA helps, right, with how much you can batch users and the throughput you get. And so I think, the same applies to OpenAI's O1, right? Like I'm going to kind of rehash stuff you've probably already seen, but like these bigger models are coming that take more flops, but they're not necessarily going to happen. That's not the only vector of scaling, right? You can scale on compute, you can have better data, but you can also have test time compute, right? I.e., you inference more, you get better model results, right? And so the important thing is like, again, with traditional inference, you have a much lower smaller KV cache because the average user inputs and gets much less output, right? In the case of O1, OpenAI is not providing you the whole output, but they are generating a ton of tokens that they're just not sending you. And then they send you some tokens at the end. And this traditional inference lets you batch at very, very high sizes, where Strawberry O1 does not let you batch at very high sizes because the KV cache starts to dominate, right? So this is sort of the same chart as earlier, but in a different way. And it's what is the maximum batch size for a 8 GPU server running Llama 405B at FP8, right? And why that's relevant is like, hey, if I'm serving one user, I run out of memory on my server at like 100 and something thousand tokens, right? But if with standard attention, right? But if I'm batching at like 64,000, then I can only do a maximum prompt length of 10K, maximum sequence length of 10K for those 64 users, right? So there is a drastic scaling, right? Because you're serving 64 users now, you're generating not 64 times as much revenue, but like something like 50x more revenue because you're serving so many more users. And so why this is really important again is because if you look at like context length versus like throughput speeds, this is also very important, right? Like when you use OpenAI's O1, it thinks for like 10 seconds, 20 seconds, 5 seconds, like it varies a lot, but it like thinks for a while and then it sends you tokens. But if you batch higher, right, KV cache is not just a memory capacity issue, it's also a memory bandwidth issue. So when you have a long prompt, every single forward pass, you must read everyone's KV cache in, and your memory bandwidth starts to decline. And the time in which you can do a forward pass is basically what's your memory bandwidth for your chip, right? So if it's, if your chip is 10 terabytes a second, right, or your server is 10 terabytes a second of memory bandwidth, and you have a 400 billion parameter model at FP8, then you can read that 400 billion parameter model, let's call it 500 billion for easy math, like 20 times a second, right? 10,000 gigabytes a second divided by 500 gigabytes for the model weights, right? But then each KV cache that you load brings that number down, right? Because that's eating into how much. So if you have 100 gigabytes of KV cache or 500 gigabytes of KV cache, now your maximum tokens per second is not 20, it's 10, right? Does that make sense? And so as you increase prompt length, that drastically reduces your speed of outputting to users. This is more of like a roofline model. Obviously, there's like inefficiencies in this calculation. In like doing this, you don't always get like the perfect number out of the chip, but you are drastically decreasing the speed. And at the same time, when you get outputs from O1, you don't want it to take like forever to get that output. So it's a very big like chicken and egg. Like I can't batch a ton of users, but I also can't. And if I do batch a ton of users, not only is the like memory going to run out on my server, but also the token output is going to be much slower, and therefore the user experience is going to suck, right? And who's going to want to use a really slow model, even if it's much smarter? So there's like multiple variations here.
Does your fixed cost of running the H100, that assumes that passive power dissipation is like way larger than active power dissipation? There's no marginal cost to run?
When you say passive power dissipation.
The chip itself. So basically, like, why is there no marginal cost of running it at 100% utilization versus at a lower
so when you look at the, sorry, I'm going to try and see if I have this slide somewhere at the bottom about the cost of a server. Somewhere around here. Yeah, here we go. So when you look at like a server, you have various different servers here. Oh, there we go. You have various different servers here. The thing you want to focus in on is probably just the H100, right? Oh no, this is the wrong chart. Sorry. Oh, we blacked it out. I'm sorry. It's okay. It's okay. It has the numbers that I want you to see. It doesn't break out networking and storage and all that, but there's the total server cost, right? So if you look at like H100, a total server costs like $270K, right? And this is for not the biggest providers, but like the next tier down. But then you look at like hosting cost, right? That's electricity cost. That's the data center cost. That's the PUE is the inefficiency of cooling it, right? Basically, PUE is a metric of how much power are you like getting into the data center versus how much is actually going to chips, right? And so like if you say a PUE is 1.35, that means 35% of your power is being lost in inefficiency of like converting it to the right, from AC to DC or to the right voltage, from cooling the chips, et cetera. And like the best data centers are like 1.1, and then like more typical is like 1.3. So you can sort of see the difference is like on an H100, your capital cost per month is like $5,000, right? But your hosting costs are like $2,000. So it's like, running it at 0% versus 100% is not even like, it's $2,000 to zero, but most of the cost is the chips itself. So your marginal cost is mostly driven by the cost of the chips, not necessarily running it at 100% or 50% or 0%. So you want to utilize it as much as possible.
Yeah, is co-location cost just the data center renting cost?
Correct, yeah. So this co-location cost can be broken out much further into like how much is the land, how much was the substation, how much was the building, how much is the like on-site technicians, all that. But that's kind of wrapped up because this is more so for like a new cloud company, not a company building their own data centers, but people renting data centers, i.e. co-location. Yeah.
So are there like non-big tech players making these massive data centers also? Or?
Yes, I'm happy you asked. There is an entire like 100 companies doing this. I'm being a little facetious, but let's see. Yeah, so this is like 50 companies in this space, right? So there's like the traditional hyperscalers, which are like the big tech companies you've heard of. These are people renting GPUs, right, as a service. This chart is. And so on the right side, you have like Google, AWS, Microsoft, Oracle. Of course, like Meta and like, some other folks are not there because they don't rent GPUs. And then you have like the Neocloud giants, which you may have heard of like CoreWeave or Lambda or Crusoe or Nebis. And they make like pretty large clusters, like tens of thousands of GPUs, right? The data center with the natural gas plant I showed you earlier is going to be roughly 100,000 GPUs from CoreWeave, right? And then there's a sea of like a bunch of other players, right? Who are, have just like much smaller numbers of GPUs or even like quote unquote sovereign AI, right? So like the Malaysian power grid company has decided they want to get into data centers and make AI data centers, right? And it's like, okay, great. Now they're going to spend $1 billion on this, right? And it's like, oh yeah. Like G42, which is like a UAE company wants to do it. And like there's all these different like sovereign companies that also want to do it. So there's a vast number of companies that are building data centers now today. And it's quite interesting. Yeah.
Can you say more about the VC clusters?
Oh yeah. Like some of these VCs have just like signed deals for their own clusters, and then they rent them to their startups at reasonable costs.
Are they actually built into the clusters?
They usually like get them from someone else. They don't build them physically. They may like claim they do, but like they rent them from other people. But like they pay for the capital cost. Like they'll buy the server and then have someone else operate it for them.
How are these neoclouds financed? Because like some of the things you're talking about are tens of billions of dollars. Yeah. And even scaling down from that, you think that it's like someone's entire funding round going into one data center.
Well, so it's not venture backed mostly. It's mostly debt and private equity backed. Because if you think about like what is the return profile for various investors, right? Like venture capitalists want like to do like 100x or 1000x on one investment, and if everything else fails, that's fine. Private equity companies and like debt holders want to make like 15% on everything they do, right? It's a very different model, but like that's where like renting GPUs may make sense. Is doing hey, like here's the breakdown of all the costs. If I have a certain margin on it, my cost for an H100 is $1.65, right? Well, if I rent it for $2, that's like a sizable profit for a long term, right? So that's it's more of like an infrastructure play, like building a road or like a port is like what the people that are investing in these neoclouds primarily.
How is the data center design? Is the design of a data center directed by the chip that you're going to be using at all, or they're like just agnostic of each other? Like if B100 starts coming, like is it going to change how data centers are built, or if you're using the AMD chip, like are you going to?
Yeah. So there is the challenge is like chips come out and the design is much faster than physical infrastructure, right? And so in the case of like Meta, they did have to redesign their data center, and they built it specifically because they knew NVIDIA's next generation Blackwell is liquid cooled and high density and all this stuff. But like a lot of folks are building data centers for the standard market, and then they're like, oh look, AI, I guess I have a data center, let me do it. So there's like comical images of like, like I mentioned earlier, like a server rack is like 12 kilowatts, right? But an AI rack could be 80, could be 100 kilowatts, right? So what do? Well, I just leave most of the data center physically empty, right? Because like space is not relevant, right? It's all about like the power and the cooling and all that. So people like have inefficient designs, but it's okay. And obviously you want to rush to like higher power density, water cooling, being able to bring water directly to the chips, etc. But there's like many different like ways of like doing stuff. So this is actually hilarious. Let me get this photo. Microsoft, what is it called? GB200 rack. Where is this thing? Sorry, I can't find it right now. OCP. GB200, OCP. Let me see. Sorry, this is past month, maybe? It's pretty new. Sorry. Microsoft, GB200, LinkedIn. They posted on LinkedIn, I remember that. I think this is the photo. I think this is the photo that I wanted, hopefully. If not, it's fine. Yeah, it's fine. That's Meta. Shoot. Oh, well. Basically, it's a GB200 sidecar. So basically, like these chips are water cooled, right? Yeah, so here we go. This is like a rack of NVIDIA GPUs, right? And this is the next generation Blackwell one in the center. And that's like 140 kilowatts. But like my data center may not have like liquid cooled ready. It might not have the permits. It might not have access to water because it's in Arizona or whatever, right? Like there's all sorts of reasons why I just don't have liquid going directly to there. But what I can do is I can stick a massive radiator next to it, right? So this is literally just like a radiator. There's no compute in there. It's just a humongous slab of metal with a bunch of water going through it to a bunch of fins, and it's just like blowing air over it. And so like, if the chips that NVIDIA designed are like super high density and require water cooling, I just stick this massive radiator next to it and now it's air cooled, right? So like this is like very frequent. Like the vast majority of NVIDIA's GB200 shipments are actually going to come with like this massive radiator next to it. Because like this is the only way to cool it reasonably in a data center that's not equipped for water cooling. Because they just started building water cooling data centers, right? They do not sell the big slab radiator, no. But they have made a supply chain of many companies that will sell them.
Yeah, but I have a question. So how does those different cloud companies differentiate themselves besides price? And also, is this server build-out sustainable in the long run? Because it just seems to be kind of overwhelming right now.
Yeah, I mean, if you think like AI is going to change your life or everyone's life, which I assume you do because you're in this class, then we're going to build more servers and make AI, right? And great economic things will happen, and suffering will end for all of humanity, right? Like, this is great. But obviously, like, the amount of spend is like skyrocketing, right? Like the big cloud companies used to spend $20-30 billion a year on servers. And like next year, Microsoft's going to spend like $80 billion, and then CoreWeave is going to spend another like $30 billion on their behalf. So like the jump is humongous. And then you do that for every single company. And then hey, there's 40 different cloud companies doing the same thing, right? Like they're not quite on the scale of like Microsoft, but like they're all spending. So it's like kind of insane. Very life changing or very infrastructure world changing. But is it sustainable? I don't know. Yeah, definitely not on a power basis. But AI will solve global warming, right? It's interesting. I don't know. I'm not the biggest believer, but I think it's possible. Yeah. I think it's a long conversation though. Sorry.
What do you feel about like there's such a big push for transformer? Do you think that is the future? Like we're gonna
what being pushed?
Like transformer architecture. Do you think that is where like the next 5 years going, or like is there going to be a big architectural change and all of the things we've been doing from the system's point of view just like fail because we have something which is like 10x more efficient, but it sucks now because we don't have efficient systems for it on the back end?
I mean, like transformers are very efficient for what they do, but like you don't get like amazing AI just by building the biggest transformer possible. You have to do a lot of other systems around it, right? And one of them is scaling test time compute, right? One of them is like generating a bunch of synthetic data and teaching like models to self-critique and all these validations and like all sorts of stuff that you can do to make the system better. Now, does it necessarily need to be a transformer? Maybe not, but it's also the most efficient thing that we've seen so far. But that doesn't necessarily mean like, so the interesting thing is like, oh, people are building all these things for transformers. Like, no, you're building 100,000 GPU clusters, and like when you're not doing the big transformer run, you're doing a bunch of experimentation. Well, it turns out like some guy at OpenAI or whatever, some person at Anthropic or whatever is doing a bunch of like tests on like, oh, does SSMs work or does this other model architecture work? And if it works, then they'll scale that instead, right? So it's like, sure, big things are being built for transformers, but like it's repurposable most likely for whatever's next. Maybe not perfectly, right? But it is repurposable to some extent. And that's why like people do want to use GPUs, right? Because while GPUs are getting more and more specialized, right? If you actually like on a microarchitectural basis, like TPUs and GPUs are getting a little bit closer. Interestingly, they're still very far apart, but like they're getting closer because like the workload is this, right? But you also want that general nature so you can like experiment and run different algorithms. And if transformers are not it, then like there's still other things that you can run well. Okay. One last question, yeah.
What are your thoughts on neuromorphic computing and using that to kind of make AI inference more efficient?
So the cool thing about like all these like biology-inspired computing designs, like brain is way more efficient than GPU, right? To be clear, at least at like intelligence, not necessarily like 56 times 12. Like no, you're bad at that, but like computers good at that. But like I think the challenge is like, how are you going to make AI that is very efficient on neuromorphic without like all of the research and all the smart people working on that, right? So there's like a freight train of like all the smartest people are writing GPU kernels for models that run and architectures that are efficient on GPUs, right? Like the arithmetic intensity and like the memory accesses and all these things. And yeah, they'll like experiment around here in this tech tree, but like here you're like here. Like there's no tech tree for neuromorphic because relatively there's not that many smart people working on it, right? Versus like GPUs and the hundreds of billions of dollars of like infrastructure being built here. And so like potentially that's a far more efficient thing if you said, hey, here's 100,000 of the best people in the world and they both worked on these, and actually neuromorphic is more efficient and better eventually. But you can't just like switch those people over, right? So in that case, it's sort of like the freight train of like progress is like, and all the money is being funneled towards GPUs and like large systolic arrays and like standard like architectures, von Neumann architecture, like all this stuff, right? So neuromorphic architecture is like just very hard to evolve and go deeper into. Like who's going to build $1 billion supercomputer with neuromorphic chips? In which case, how are you going to even get a model that's like reasonable? Or how are you going to get a bunch of researchers who have time to experiment?
Okay. Thank you.